Hey students, let's solve 11C now here. We have this collision. And of course, like all these problems, this can get a hard one because anything that involves, I think, rotational mechanics is hard. And this has two things. This is based upon the linear motion and rotational motion, both momentum, the linear momentum and rotational momentum. It doesn't have the third piece, which is conservation of energy. That would make it even extra hard. And there's a lot already about part two that's hard. But let's start here with part one. Part one's not too bad. It says here we got a green and a blue rod of equal mass and of height 2 centimeters. So kind of in this picture here, they approach each other so that their ends touch and stick together. Initially, the green rod is moving at 4 meters per second to the right, and the blue rod is moving 2 meters per second to the left. After the collision, the two rods then stick together, travel translationally to the right, so they kind of hit right here, and then travel to the right, and that's the first part of this. They also then spin, and so they're tumbling over each other. Let's see, do I have anything that looks like two cylinders that I could kind of draw, maybe? Here we go. Here's cylinder 1. And cylinder 2. So, oops, they didn't really stick real well together. Maybe I'll just do that. But here's the idea. If I have the green one moving and the blue one, they come in right like this, and then they hit, and then they spin like that. And so that's the motion that's going on. And the first part of this one is just translational motion, which tends to be way easier than the rotational stuff. And just as says, the initial momentum is equal to the final. In fact, I hope as soon as the word collision was brought up, maybe in here and here and here, or the fact that they approach each other and stick together, you're thinking momentum, because that was my clue to you that, hey, anytime you have this collision, this interaction, here's what we know is the momentum is conserved. And in this case, we've got both going on. But let's start with the linear momentum, because that's what part one is all about, because it says, what is the translational speed? So it's not asking about rotational speed. That's coming up. And so this just says, all right, so let's take the mass of the green one. We'll call it m. We don't know what it is, and speed of 4. And the blue one, mass m, speed -2. That would be the momentum before the collision. Then after the collision, we have this. They stick together, so the mass is 2m, and they're traveling with some speed v unknown. So there's the principle of conservation of momentum. And you can see right away that there's an m in each term, so those can cancel off. This becomes a 2 and a 2v, and then the math comes out real simply, just 1 meter per second. So there's the part A, I'll call it the easy piece. All right, let's go to part B, or I guess it's part 2. What's the rotation? And same logic, except this time, since we're talking about rotational things, we're going to do the angular moment. And so the angular momentum is conserved. And thinking of the before the collision as having an angular momentum is a little tough. That's why we did a lab on it. And I said that one of the toughest things of rotational motion, and everything about rotation's tough, but one of the even tougher parts of it is to think of something moving in a straight line as having angular momentum. So maybe a review here is in order, and I'll do it with the shape of a cylinder. But if the cylinder is moving along, we could say the angular momentum is r cross p. And so in our case, since they're going to collide and stick, and then after they stick, they spin around their center of mass, the R part we're interested is about half the height of the cylinder, which height of the cylinder is 2 centimeters. So we're going to be looking at 1 centimeter. But you might remember us going through there. The magnitude then comes out just to be R, and then the momentum is mv because the angle is 90 degrees. And so we usually write this as mvr for the angular momentum of something going in a straight line, at least the magnitude, and we won't worry about plus or minus quite yet. Now, in our case, if we take this as the first cylinder, so imagine this the green one here, and then this is the R. If I take my right-hand rule, it's going to be R cross P, and my thumb's going to go into the board. And so usually we consider that negative. And of course, it's you can kind of see that if you were to catch it here, it would kind of tend to make it rotate around in a clockwise direction, which is negative. And by the way, the one underneath it, sticking to it, the blue one, would be doing the same thing. It would tend to rotate around also. So both of these have an angular momentum that's kind of hard to see until they actually hit. That's why I say this is kind of hard to visualize, that things going in a straight line have an angular momentum. And it's clockwise. So I'm just debating if I should stick to traditional negative on that or just call clockwise positive. Now maybe I better stick to the negative. So let's do this. So let's go L initial before. And let's just say it's twice then the L of the green one. So in other words, whatever the green one has, the blue one also has. All right, so 2. And then the magnitude is this MVR we just talked about, and the sign was negative. So I would say the initial angular momentum of both the green and the blue cylinder is a -2 times their mass, which we don't know what that is. Oh, my deep apologies here. They don't have the same speed, so I should not do that. Okay, let's try that again. So the L initial is the L of the green one and the L of the blue one. Okay, so the green one would have a negative. It would have M. The velocity would be 4, and the radius, which I'll put in meters, would be 0.01. The blue one would also have a negative, and a 2 and a 0.01 also. And so the total angular momentum is negative clockwise. It's an M, and it looks like this would be a 0.04 and a 0.02, which make 0.06. So that's how I would mathematically describe the angular momentum before the collision. And like I said, that's probably a hard part, because then the angular momentum after the collision is just I omega. And we're just going to then come to this picture and think of it as this longer rod that is now 4 centimeters long and then spinning. Okay. So if I go to the book here on my screen, and I guess it's section 3 of chapter 10, I see that a rod spinning around its center is 1/12. And let me just put mass, length squared, and then omega. Because using the symbols in this problem, since the two stuck together, the mass would be 2 times little m. See, because I used the little m to represent the mass of the green and the blue one. And now I'm visualizing them stuck together. So that mass of this new rod would be 2m. And the length of this would be 0.04 squared. And so now setting these two equal together. Oh, and it would be rotating clockwise. So I guess I should watch my sign. So the initial equaling the final would look like this. Negative m.06 would then equal a negative, and I'll put that m. Let me do a little bit of math here. Let's see. This is a 2 over a 12 times a 0.04 squared. And so this is going to be a 2.66, I'll call it 7, times 10 to the negative 4 omega. So the negatives cancel, the m's cancel, and now if we just do the 0.06 divided by that last answer, we get 225 radians per second for that angular speed. So again, hard one, real hard one, and hopefully you did somewhat decent and got a lot of partial credit, if not fully, on this one. All right, take care.